Welcome back to Pike Mathematics. Today I want to talk about logarithms, and this video is meant to be a follow-on from a video I did last week on exponential functions. So let's get started. I've already created this paper that we can work in. So let's start with the definition. If we have this exponential function b to the x, and b is greater than 0 but not equal to 1, then there exists a function, an inverse function, which is called the logarithm of base b. Now logarithms are quite easy to work with in Iota. If you want to do a logarithmic function, this is all you have to do. You type log, parentheses, and now you have to tell what the base is. So symbolically, we'll say that's b, and then you have to tell what the variable is, x. And there you go. That's how you work with logarithms in Iota. Um, if if you did not tell the system what the base is, if you just typed, say, log of x, that's fine. You can do that. What the system does is it just automatically assumes that the base is 10. Well, what about in the instance where the base is Euler's number, or E? Well, that's known as the natural log. So we have that function programmed into the system as well. To use that, all I have to type is ln of x, and you can use the natural log function that way. One caveat is that with the number, the constant E, if you want the constant in Iota, you have to type add E. That gives you the constant. Or if you want the exponential function e to the x, you type exp parentheses x. And that's how you can utilize e to the x. So in general, the system doesn't fully understand the significance of the letter e, but there are some exceptions to that. For example, we've programmed it to understand that the natural log of e is 1. And we've programmed it to understand the natural log of e to the x is equal to x. So E is treated a little differently than some of the other letters of the alphabet. Okay, so logarithms are inverse functions of exponential functions. So that means if I put x into an exponential function and it spits out y, if I have the inverse of that exponential function, if I have its logarithm, if I put that y back into the logarithmic function, it should return x. And so let's demonstrate that with a couple examples here. So let's say I have f of x, and we'll set it equal to 10 to the x. And then we'll make the inverse of that, which is the logarithm base 10 of x. Okay. So if I take f of 1, what do I get? I get 10. So if I put 10 into g, what will I get? Hoping 1. We do. Okay. Let's try something a little different. Let me delete these guys. And then I'm going to change the basis here. All right, so I made those changes. So now I got to hit refresh. I changed the base to 6. So what if I have f of 3? What does that give me? 216. So if I take g of 216, I would hope to get 3 back. Let's see. All right, so I just wanted to do that to illustrate the inverse relationship between exponential functions and logarithms. All right, let's look back at this logarithm of base b. We know that it's the inverse of an exponential function b to the x, but beyond that, like what is this? What's it telling us? I always had a really hard time with that until I started basically translating this into something else in my mind, and that greatly helped me understand logarithms. And this is what I do. So if I see logarithm of base b of x, this is what I change it to in my mind. And bear with me a little bit as I have to use our text editor here. Do that. Let's see. Okay. So when I see this, in my mind, I change it to this. And so this is basically saying b raised to what power equals x. And that's what the logarithm is telling us. It's telling us what power you would raise b to in order to get x. So let's do some numerical examples. Let's say I was working with 10. Again, I'll use that text edit. And so now this might come a little more into focus. The question is 10 raised to what power equals 100? Well, That's 2. 10 squared is 100. And we can illustrate that, or we can demonstrate that taking the logarithm of 100. There you go. Let's do one more example. Okay, so here, 5 raised to what power equals 125? Well, we can take the logarithm base 5 of 125 and we'll get that answer. It's 3. So 5 cubed equals 125. So I don't know if that helps you, but for me, this helped me to kind of understand what it is that logarithms were doing. Okay, I think to further conceptualize logarithmic functions, I think it would be a good idea to graph a few. So I'm going to use this graph that we did in the previous video where we graphed the exponential functions. So now I'm going to graph the logarithms associated with these exponential functions. And so if I click on this graph, this will pop up and I hit insert function. And now I can go ahead and start graphing the logarithm. So the first thing we graphed was 2 to the x. So I am going to graph the logarithm of base 2 of x. And we'll put that in blue. Oops. There it is. Okay. The next one looks like the base was 2.25. And we did that one in this aqua pendant. There you go. And the next one was e to the x. So the inverse of that is the natural log of x. And so you can just use ln parentheses x. And we did that one in green. Okay. Then we did 4 to the x. So that would be log base 4 of x. Yellow. Okay. And then we did 10 to the x. So the logarithm of base 10 would be next. But instead of typing in base 10, we're just going to do log of x to demonstrate that you don't need to put in a base when the base is 10. Oops. Let's see. There we go. And last but not least, we're going to put in this base 100. See what happens. There you go. So here are the exponential functions, and here are all their inverse logarithmic functions. So I really liked when we made this the last time. I liked this graphic. I really like it when you put it all together. I think it's quite pretty. And I hope that graphing it helps you also to kind of understand how the logarithms work. Okay, next, let's talk about some properties of logarithms. First, let me close this out. And this. Okay, here are the properties. If you've seen these before, that's great. If you haven't, though, I highly recommend committing these to memory. There are so many times when these properties can help you either simplify a problem or outright solve it, that it's worth memorizing these. And but for these 3 properties to be true, we need x, a, and b all to be positive real numbers. X can't be equal to 1, and c down here has to be a real number. So what's the first property? It says that the logarithm of a times b is equal to the logarithm of a plus the logarithm of b. All right, let's demonstrate that. What if I take the log of 15? What is that equal? 1.18. Well, 15 is equal to 3 times 5, so I ought to be able to take the logarithm of 5 plus the logarithm of 3 and get the same answer. Let's see. There you go, 1.18. All right, so what about this next property? It says that the logarithm of a over b is equal to the logarithm of a minus the logarithm of b. So let's try the logarithm of 9 divided by 3. What does that give us? 0.48. Okay, what's the log then of 9 minus the log of 3? There you go, they're the same. And this third property, I find this one probably the most useful. Okay, so it's saying that the logarithm of a to the c is equal to c times the logarithm of a. Let's try an example. What if we have the log of 2 to the 5th? Oops. What does that equal? 1.15. Okay. If this property is true, then 5 times the log of 2 should equal 1.51. And it does. Um, Again, this last property helps me oftentimes to solve equations. And here's another good example of it. Let's say I had 3 to the x equals 81. And I'm going to use our text editor to format that in a better way. There we go. So let's say I've got this. 3 to the x equals 81. Well, that would be equivalent if we take the logarithm of each side of this equation, then we can bring this x down and we kind of isolate it and solve for it. And kind of the cool thing about using this trick is that you can use the logarithm of any base. So what if we used the natural log? So if this is true, then we're going to take we would say that x times the natural log of 3 equals the natural log of 81. And remember, because we're taking the natural log of this side, we also have to take the natural log of that side. So that's what I'm saying here is that x times the natural log of 3 is equal to the natural log of 81. And so if that's true, that means x equals natural log of 81 divided by the natural log of 3. What does that give us? Let's see. 4. Okay. So what is 3 to the 4th power equal? There it is, 81. So I think that's a great way to solve for variables that are in the exponent. Okay, I'd like to finish up this video with a real life example of logarithms. And that's this equation right here. This equation is the equation for calculating the number of decibels as a function of the intensity of a sound that you're hearing. So the decibels are equal to 10 times the logarithm, this is log base 10, of x, and here x is the intensity of the sound you're hearing, divided by I naught, which is the intensity of the lowest sound the human ear can hear. So let's play with this a little bit. Let's say I hear that lowest sound that my ears can pick up. How many decibels is that? Well, I've created this function. It's a function of x. So what if I make x this I naught? How many decibels is that? 0. Okay. What if instead I hear something that's 10 times the lowest threshold? So 10 I naught. And I'll go ahead and put some parentheses around that. What do I get? All right, it's 10 decibels. So it's the sound is 10 times more intense, and so the decibels jump from 0 to 10. Well, I've been to football games where they'll have this kind of gauge on the scoreboard that shows how loud the stadium is. And sometimes that goes over 100 decibels. My question is, how intense does that sound need to be to reach 100 decibels? So the equation would look something like this. 100 decibels is equal to 10 times the logarithm of x divided by I naught. And I'm going to use our text editor to kind of clean that up a little bit. There, that would be our equation. And we're trying to solve for x. Well, first thing I'm going to do is I can divide both sides by 10 to clean this up a little bit. And so I'd have this equation. Okay. All right. Now let's use what we know about logarithms and exponential functions, that they have inverses. So this is log base 10, which means it's inverse. The inverse of log base 10 is 10 to the x. So what if I take 10 and raise both sides, make both sides kind of the exponent of 10 to the x? Well, that would give me on the left-hand side, I would get 10 to the 10th. Now, if I take 10 and raise it to the logarithm of x over I naught, well, 10 to the x and log base 10 are inverses. They'll just cancel each other out. And so all I'm left with is this. Okay. So now all I have to do to find what the intensity is of this sound that results in a 100 decibel reading is multiply both sides by I naught. So I've got, what is it, 10 to the 10th times I. What is that? There we go. And again, this is intensity. It's in watts per meter squared. So it's 1 over 100, which is 10 to the negative 2. Now let's look at this. That lowest threshold that the human ear can hear is 10 to the negative 12. That means that this sound here that results in a 100 decibel reading is actually 10 billion times more intense than that lowest threshold. You can just see it here. If I take 2, 3, 4, 5, 6, 7, 8, 9, 10 times I underscore 0, we'll get the same answer. So I think that's interesting, and it just shows the nature of logarithms. That you'll recall that when we did this example here, where we went 10 times that lowest threshold, we went from 0 all the way to 10 decibels. But then we had to go a billion times more intense than this to get up to 100 decibels. And so I think that demonstrates the behavior of logarithms. I really hope you enjoyed this video. Please stay tuned for future videos. I've got many, many more planned. If you haven't been to the website yet, please go there. It's pikemathematics.org, and we look forward to hearing from you. Thank you so much.